Presentation 07. Polarization analyzed small angle neutron scattering of magnetic nanoparticles.
Yep.
Presenters Kathryn, Hasz, Liv Deedon, and Yumi Ijiri, Department of Physics and Astronomy, Oberlin College, Ryan Booth, Sarah Majetic, Carnegie Mellon University, Julie Borcher, Kathryn Kricka, NIST Center for Neutron Research, and Jim Ryan, Los Alamos National Lab. And the speaker is Kathryn.
So as was mentioned, I'm going to be talking about my work with small angle neutron scattering on magnetic nanoparticles. So first, why are we interested in magnetic nanoparticles? Well, magnetic nanoparticles are very useful in a lot of very practical applications. First off, we can use them as a potential for data storage. If we use the magnetic moment pointing either up or down as either a 1 or a 0, we can encode binary. And since magnetic nanoparticles are very small, if we have them in a nice ordered array such as this, we can store a lot of data in a pretty small spot. But before we can do such a thing, we have to understand a lot of the magnetic properties of the nanoparticles and how they interact with each other, so we don't have the moments of the nanoparticles spontaneously flip, because if that happens, all the data would spontaneously disappear. That wouldn't be good. Biomedical applications for such nanoparticles. If we have a targeted drug delivery system, we can have medicines go directly where they're needed in the body, as opposed to wandering around through the blood system and getting stuck either where they're not needed or potentially harming someone if it's a drug that's potentially toxic. By injecting nanoparticles into the body with a magnetic core with a sensitive outside on them, and then some sort of medicine attached to the outside, like an antibody or whatever's needed. And then by putting a magnet outside of the body, that can bring the nanoparticles directly to where they're needed, as opposed to going through the rest of the bloodstream. They're also a possible cancer treatment. If nanoparticles are injected into a tumor, then a field can be cycled back and forth quickly outside of the body, and then heated, and then the nanoparticles move back and forth and heat the tumor, killing off the cells through hyperthermia. But before any of those things can happen, we need to ensure the safety of the particles, uniformity of them, and a high magnetization. So before we can use these applications, we have to understand the materials themselves. Because these materials, while we understand them in bulk, we don't understand them on nano-length scales, in which they can have very different properties. We also have to understand their magnetic properties before we can use these applications. So we've been working with a system of iron oxide particles. This is a canonical system of a simple ferrimagnet, which means it's just one chemical system as opposed to a core of one type of metal and a shell of something else, or something like that. These were synthesized by reaction of an iron precursor, and we found that they had a particle size of about 9 nanometers through a TEM image, such as the one shown here. We prepared these into a 3D ordered version by redispersing our chemical solution of iron oxide particles into toluene, and we were growing them into 3D crystals. And we grew them for a month and got them into a powder. These samples were sealed into aluminum cells for our measurements. Our measurements were done using small angle neutron scattering. This method was done at the NIST Center for Neutron Research, the NG3 beam line in Maryland. There, the neutrons were scattered at 5 angstrom neutrons were scattered off of our sample, and we detected them with a 2D detector. Our detection looked something like this, where the bright spots, such as the yellow, were a lot of counts, and the dark spots out here were very few scattering counts. This is like a reminder of Bragg's law, where 2D sine theta equals n lambda. But we don't like to work in such things as d or theta. We work in Q space instead, where the relations are as shown. So the magnetic and the structural characteristics of our sample determine how things scatter. So it's sensitive to both the actual crystal structure and to the magnetic effects of our sample. So we worked at temperatures from 5 to 300 Kelvin and fields from 0 to 1.2 Tesla. We worked with a specific type of small angle neutron scattering using a polarized neutron beam. In this, we selectively chose what direction the neutrons were pointing both before and after our sample. before we used a supermirror to polarize the beam by bouncing the neutrons off and using Brewster's angle, and a spin flipper to select the state, either up or down, before the sample. So we used a supermirror and then a flipper. Then we had our sample. Then we had a helium-3 cell, which is shown here, and an NMR in situ flipper after our sample to select, again, up or down. So using that, we got 4 possible states, either up, 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 down, down, up, or down, down. So by combining these 4 possible states, we were able to isolate components of magnetic scattering, both parallel and perpendicular to our applied magnetic field. So when we analyzed our data, we were taking sector cuts of our 2D data, that big, nice circle, and extracting relevant behavior to get 1D data, nice, normal graphs like you would expect. For our sample, we had isotopic structural scattering, which means it didn't matter what angle we took our cuts at for our structural scattering. Our crystal was the same no matter what, in structural world. In magnetic world, it did matter. But because of that structural scattering and our geometry, our equation simplified to the following. We have n squared, which is our structural scattering, dependent only on our up-up and our down-down scattering, and is proportional to our intensity. Our perpendicular scattering is proportional to our up-downs and our down-ups, our spin-flip scattering, because we're flipping what direction the spin was in between. And then we had 2 relevant equations for our parallel scattering, one of which was completely independent of any other equations. Our other one was dependent on our structural scattering. Using those equations, we found some interesting results about our iron oxide nanoparticles. At high temperature and field, we found that both our structural scattering and our parallel scattering, magnetic parallel scattering, looked the same. They both had a nice peak right around about 0.8 Q, inverse angstroms. And that peak corresponds to a cluster of nanoparticles working together and working the same way. And even though those peaks have very different intensities, they have the same general behavior. However, our perpendicular scattering had a very different shape. It has a nice dip as opposed to that peak. That dip corresponds to a single shell model. And because that dip is opposite of our peaks, we got the idea that there's a canted magnetic shell model, which means that there's one direction, which is our general magnetic moment, and then on the outside, there's a shell, which has magnetic moments pointing in the opposite direction, as seen here. Lately, what I've been doing is investigating how that shell evolves as we apply different magnetic fields, because we found that shell when we were at high field and temperature, but we want to know what happens when we're working at intermediate fields. And actually, we found that that shell is here shown in the purple. And that's true when we're at high field. But when we get to lower fields, such as the red, which is an intermediate field, that shell starts to disappear because the dip starts to decrease. Then when we go to a very low field, such as shown in the blue, that dip isn't even present at all. That shows that that shell that we had is a solely magnetic effect. We don't have it at all in the structural data, but it's only a magnetic shell. We've also found that when we get to lower fields, we have a lot more scattering here in our lower Q region, which is that lower angle. I've also been taking a look at how to extract the parallel scattering in different ways and what effect that has. We've seen that the parallel scattering grows as we increase the field. Here our low field again, and our intermediate field, and our high field have different intensities. And this component of it is the one coherent with our structural scattering. And that one looks different than our part that is incoherent, or is not dependent on our structural scattering. This one that is not coherent with our structural scattering has additional structure. It has this nice little peak here that is not shown in this one. So we're trying to figure out why that happens. there's this additional order from this peak, because the peaks show order, that's not present when we look at what's going on with the structural order, which means that there's more magnetic order present that's not present in the crystal structure itself. So in conclusion, we've successfully used polarization analyzed small angle neutron scattering to extract some fundamental properties of these nanoparticles. And we've seen that our iron oxide particles have a magnetic core and shell at high field. We've also seen some of the evolution of how this shell happens as we change the field conditions. And we've seen some additional structure, or some additional ordering within the magnetic structure that is not present in the actual physical structure. In the future, we'd like to work to characterize these additional peaks and investigate more temperature and field conditions. We'd also like to generalize this picture to other systems, such as a manganese oxide system. And I'd like to thank the NSF grants that I've been working with and my advisor, Yumi Ijiri, who couldn't be here today. Thank you.
Questions of the speaker?
So is the existence of the shell expected theoretically, or is this a surprise, or what?
Theoretically, we've seen some evidence of other particle systems actually having a physical core shell model, and other ones have seen different types of shells. I don't know if we've seen any others with a core and a shell that's solely magnetic, but I don't know. I actually wasn't around when we discovered the core in the shell. That was, I think, about a year or two before I got here, so I'm not 100% sure.
Can you remember when the field is being applied? Is it applied when the sample is cold, or do you apply it?
We've been working, these are field-cooled samples. So the field is applied, and then it's cooled.
Do you get any sense from the neutron data of like what fraction of the nanoparticle is occupied by that shell?
The shell is much smaller than the core. Trying to remember, I've just been working with the manganese version of this, and that has the magnetic shell is much larger because there's actually a physical shell as well. In this one, I think the shell is somewhere along the lines of, I can't remember the number off the top of my head. If you really want to know, ask me next week or something.
And does it mean that that extra structure you're seeing a larger cube in the last picture? So we're allowed to think that there's something spatially happening on a shorter length scale because of that larger cube?
This peak?
Yeah.
We're thinking that there might be actually in the magnetic ordering that the magnetic nanoparticles are working together, because that peak isn't in the structure. That one's just the way that they're conglomerating in a magnetic sense. So we're thinking that the magnetic domains are working together in certain ways, and even though the structure is not working together as much, that that is like the magnetic domains are bunching together further than just the actual nanoparticles are bunching together. So there are bigger conglomerations in the magnetic domains than there are in just the particles themselves.